We now move into an important topic in compound semiconductor physics and optoelectronics, that is, lattice-mismatched and pseudomorphic materials. As you can see on this section title page, this topic sits within our broader discussion of semiconductor materials, especially compound and alloy semiconductors. So up to this point, we have discussed elemental semiconductors like silicon and germanium, and then compound semiconductors such as gallium arsenide, indium phosphide, and their alloys. Now we take the next conceptual step. What happens when we try to grow one crystalline material on top of another material whose lattice constant is not exactly the same? In real device fabrication, especially in optoelectronics, we almost never work with isolated bulk crystals. Instead, we grow thin crystalline layers on substrates using epitaxial techniques such as MBE or MOCVD. The moment we stack two different materials together, lattice compatibility becomes a central issue. It's very critical. So there are three key questions that will guide our discussions in this section. The first one is, what does it mean for two materials to be lattice matched? And the second one is, what happens if they are not perfectly matched? The third question is, how can we engineer a round lattice mismatch in order to fabricate high-quality devices? So this topic is fundamental for heterostructures, quantum wells, light-emitting diodes, laser diodes, and high-speed electronic devices. In fact, much of modern optoelectronics is possible precisely because we learned how to manage lattice mismatch intelligently. So with the motivation in mind, let's move to the next page. Let's begin by understanding the word epitaxy. When we grow an epitaxial film on top of a crystalline substrate, the atoms in the film attempt to align themselves with the periodic structure of the substrate. The word epitaxy, as mentioned on this page, means the growth of a single crystal film on top of a crystalline substrate that mimics the orientation of the substrate. In ideal lattice-matched epitaxial growth, the lattice constant of the film, denoted by A sub f, is equal to that of the substrate, denoted by A sub s. In this case, the two-dimensional unit cells at the interface are continuous. There is no strain at the boundary, and the crystal structure transitions smoothly across the interface. Now, to quantify how different two lattice constants are, we define the lattice mismatch, or misfit, as shown in this expression. So it is equal to the lattice constant of the substrate minus that of the film divided by the lattice constant of the film. In practice, we rarely achieve exactly zero mismatch. However, if the magnitude of the misfit is smaller than 5 times 10 to the minus 4, we generally consider the system to be effectively lattice matched for practical purposes. A classical example is the aluminum gallium arsenide and gallium arsenide material system, which is extremely important for optoelectronic devices. At this point, you may wonder, why is lattice matching so important? Because lattice mismatch introduces strain. If the mismatch is too large, the film cannot remain coherently strained and will relax by forming dislocations. These are called misfit dislocations, and they act as non-radiative recombination centers in optoelectronic devices. In light-emitting diodes and laser diodes, dislocations significantly degrade efficiency and reliability. So in many applications, nearly lattice-matched epitaxial growth is desired to minimize crystalline defects. Alright, so at this point, you should conceptually understand the following. The first one is lattice-matched growth usually lead to minimum defects. And if there exists large mismatch, strand relaxation can lead to dislocations. And also, device performance is strongly linked to crystalline quality. Okay, then what if we want to use a material whose lattice constant is really different from the substrate? That will bring us to the so-called graded epitaxial growth. We're going to talk about that on the next page. Before delving into graded epitaxial growth, we need to fill in some gaps here, including pseudomorphic epitaxial growth, strand, and misfit dislocations. So far, we have discussed the ideal case of lattice-matched epitaxial growth, where the lattice constant of the epitaxial film is equal to that of the substrate. In that situation, the atomic rows line up perfectly, and no strand is introduced at the interface. But in many practical semiconductor systems, we do not have perfect lattice matching. The lattice constant of the film and the substrate are often slightly different. Now the question is, what happens when a material with a different lattice constant is grown on a substrate? At the very early stage of epitaxial growth, when the film is still relatively thin, something interesting can happen. Instead of immediately forming defects such as misfit dislocations, we're going to talk about that later, the film may elastically deform in order to adapt to the lattice structure of the substrate. In other words, the atoms in the epitaxial film are stretched or compressed so that the spacing between atoms parallel to the interface becomes equal to that of the substrate. This situation is called pseudomorphic growth. The term pseudomorphic literally means false shape. The film adopts the lattice shape of the substrate, even though its own natural lattice constant is different. So let's take a look at the diagram shown on the page. The substrate has lattice constant A sub s, while the natural lattice constant of the epitaxial film is A sub f. During pseudomorphic growth, the lattice spacing parallel to the interface is forced to match that of the substrate. That means the in-plane lattice constant of the film effectively becomes that of the substrate. So we have A sub f parallel equals A sub s. Because the film is forced to match the substrate spacing, the lattice inside the film becomes strand. That is to say, they are pulled, stretched, or compressed in a forceful way. This strand is incorporated into the crystal coherently, meaning the atomic rows remain continuous across the interface, as you can see here. So in a coherently stranded structure, the interface remains perfectly ordered, without dislocations or broken lattice continuity. However, there is an important limitation. Elastic deformation stores strain energy in the crystal. As the thickness of the film increases, the total elastic strain energy also increases. Eventually, the system reaches a point where maintaining coherent strain becomes energetically not possible. So when that happens, the system relieves the strain by forming misfit dislocations, which we will discuss shortly. But for relatively thin films, pseudomorphic growth can be maintained, and this strained state is actually very useful in semiconductor device engineering. For example, strained layers are widely used to modify band structures, enhance carrier mobility, and improve optical properties in modern semiconductor devices. So the key idea of this slide is that a thin epitaxial film can elastically deform to match the substrate lattice, resulting in the so-called pseudomorphic growth with coherent strain. Now that we understand pseudomorphic growth, let's look more closely at the types of strain that can occur in the epitaxial film. The type of strain depends on the relative lattice constants of the film and the substrate. Recall that we defined the lattice mismatch parameter as A sub s minus A sub f divided by A sub f, where A sub f is the lattice constant of the epitaxial film, while A sub s is the lattice constant of the substrate. Depending on the sign of this mismatch, the film can experience either compressive strain or tensile strain. So let's first consider compressive strain. Compressive strain occurs when the natural lattice constant of the film is larger than the lattice constant of the substrate. So we have A sub f larger than A sub s. The corresponding mismatch parameter f must be negative, because the film naturally prefers a larger atomic spacing, but must match the smaller substrate spacing at the interface. The film lattice is compressed in the plane of the interface, as can be seen in the diagram here. An example shown on the slide is indium 0.7 gallium 0.3 arsenide grown on top of a indium phosphide substrate. A sub f is approximately 5.95 angstroms, while A sub s is about 5.87 angstroms. Since the film lattice constant is larger, the film must be compressed laterally to match the substrate. When this happens, the lattice spacing in the direction perpendicular to the interface, which is in this direction, usually expands slightly. So we see that the height of the lattice shown here is slightly larger than that right here. Okay, so regarding tensile strain, tensile strain occurs when the natural lattice constant of the film is smaller than that of the substrate. So we have A sub f is smaller than A sub s, corresponding to a misfit parameter f larger than 0. In this case, the film atoms naturally prefer a smaller spacing than the substrate atoms. But during pseudomorphic growth, the film must match the larger lattice spacing of the substrate. As a result, the film lattice is stretched in the plane of the interface, producing tensile strain. So we see that the width of the unit cell shown here is larger than that of the unit cell shown here, while again, because of lattice effects, the lattice spacing in the direction perpendicular to the interface usually becomes slightly smaller. So the height of the unit cell shown here is smaller than that of the unit cell shown here. All right, so the next question is why strain matters. These strain states are not only structural features. they strongly influence the electronic and optical properties of semiconductor materials. Strain can modify the following properties, including bandgap energies, effective masses, carrier mobility, and optical transition energies. In reality, these properties are mainly determined by the energy band structure of the material. For example, strand layer engineering is widely used in high-speed transistors, quantum well lasers, and advanced CMOS technologies. So rather than being merely a problem caused by lattice mismatch, strain is often used as a powerful tool for device design. Okay, so as we already mentioned earlier, coherent strain can only be maintained up to a certain thickness, which is termed critical thickness. Once the film becomes too thick, the accumulated strain energy becomes large enough that the crystal relaxes by forming the so-called misfit dislocations at the interface. So in the next part of our discussion, we will briefly examine how and why misfit dislocations form and how they help relieve lattice mismatch strain.